Take it easy, everyone. We'll go easy. Let me just, I won't separate this. We can have two different screens. Is the letter okay?
If you want, I can show them how to set up the environment and you can continue with the presentation.
It's okay, it's okay. Esteban has an error. So there is something important that we need to ensure. So you have two notebooks. One is the notebook meant for compilation. It has to be loading the Python JHub kernel. If that kernel is not loading by default using the compile notebook, then please, what I suggest is to shut down the kernel and change the kernel to Python JHub. Okay, so let me show you how I did it. I shut down the kernel, and then
is Python is batch.
no, but
Python
to compile,
okay.
it's better this Python JHub.
Okay.
And for execution, it's Python sbatch. Okay, again, shut down, and then you reload the Python 3 sbatch kernel. Remember that in Python notebooks, this exclamation sign tells us to run from the terminal. Okay. Actually, it spawns to the bash process. This comment here. Can you show me the error, Esteban? Can you show me the error, dear Esteban? So it's a glibc.
I discovered that the error is because I tried to execute locally, not using batch. Okay.
Okay, yes. So before all of you try this one, this is why I split divide and conquer again. So one notebook is to compile, the other is to execute. To execute, we will be using this script submit omp2. Okay, it has to be specifically submit omp2, and I will explain what this 8 is. Okay. Runs okay, everybody? So perfect. So let's open up the code. So I have some, okay, so I have some headers, which perhaps most of you already know them. IOStream, FStream for file, CMath, which is for math computation, complex if you're using complex functions or complex and number definitions. Random for random numbers, we will be using a random exercise later on. Vector and array, this is actually meant for those of you who like the vector and the array library, especially, for example, for statically defined arrays. The algorithm, I just left it there just in case. But let us begin with the most relevant part. So you already know using namespace standard, so we don't have to place standard colon before cout. So the first command that we'll be running is info openmp. I see that nobody else has had issues currently, so we can proceed. So I think we can proceed in the meantime while we delve into our first example, because I would like to explain, for example, what this function info openmp does and what the rest of the program does. So there is an input file that I created. It's called defs.h. And this defs.h defines a region which is specifically meant when openmp is enabled. So when openmp is enabled, the compiler creates an environment variable called underscore openmp and defines this variable. When it defines it, it actually is telling, for example, us that openmp is enabled, that the compiler is understanding the openmp directives so that we can exploit them. In order to use it, I mean, we can actually use them straight out of the oven. But if we would like to use, for example, the library implementations like functions, etc., we need to load this, we need to include this omp.h file, which has all the declarations of the functions that we'll be using openmp underneath, so that we can make, for example, function calls to determine the number of threads that we have, etc. Oh, I also defined this true false just for easiness. And here I define a function called info openmp. Just in case, this definition is because in our program we have in our code hostname we have this function call omp get thread num. So if, for example, openmp is not implemented, we need to redefine it because actually this library is not defined. So it will actually throw an error when we compile it. So that there is no error, I just define this as a function 0, okay? Well, and then we define the function info openmp. Now, what does info openmp does? It just prints out if openmp is enabled, what are the number of threads that we have enabled, and also it tells us what is the API specification version. Now I created here an unordered map with all the specifications and all the different API versions for openmp. So we have 2.5. So each of these, this variable openmp actually has this parameter here. And it depends on the data, it will actually load the different specification because different specifications have different functionalities. Well, where different functionalities are backwards compatible. It means that if you build up code using openmp with specification 2.5, you can actually recompile that code using openmp specification 4.0, which is a very important design into the openmp API specification. If all else fails and openmp is not defined, it will actually print out that OMP is disabled. So let us go ahead and run it. So let us actually, allow me to comment out all of these lines and let us compile. So in order to compile, we will be using the C++ 11 specification, although we can use 17 with no problem, or 20 if you would like to keep up to date with the latest of the development of the C++ standard library. We will fire up to warn us about all types of errors that can occur. This is good and this is bad. This is bad if you don't like warnings, but this is good if you like your code to be as clean as possible. Then we specify the CPP file and the output, we will call it exe. And this little flag here in the end, the fopenmp, will tell GCC that we will be using openmp so that it will enable capturing the openmp directives. If I remove this, for example, and I compile it, let's see what happens. It's taking a little while. Let's hope it runs fast. Oh my God, no kernel. Oh, I'm sorry. I think the problem is that it has no kernel. Let us restart and clear the output. Okay, connected. Perfect. There it is. Now it compiled. Now we have, for example, if we could do an ls, it will show us exe file there. And now to execute, we will go here and we will use our script just as you did with Professor Carlos. But in this case, we will be using two parameter strategy. So the first parameter is the number of cores. Okay, so let me comment this out just in case. So submit OMP2. So this is num cores, and this is the execution statement. So what this does is actually it submits the code. You already know that. It submits, let me restart, I'm sorry. It submits to the queuing system the execution of .exe along with other bits and pieces. So let us show. So since we're not running with the flag fopenmp, then we will not be able to exploit parallelisms. So the best thing that we can do is only use one core. So let's run it. So as you can see, it's openmp disabled. Now, if we change here and add -fo openmp and recompile it and rerun it again, perhaps this time we would like to use, for example, more threads. Here it is. So we have that it actually compiled. I have actually a problem which I would like to defer to my fellow comrades and experts. If you see the number of threads is showing is only 1. But actually, if you look into the definition of the function, is actually loading up this function omp get num threads, which, by the way, should say 2. Anyway, this is missing, but we will see that this small hiccup will not actually affect our results later on. It's actually forking the number of processes as the number of CPUs or cores that we are actually requesting to the scheduler. Okay, so don't pay attention to this error. It should not be an error. I don't know why it is there. Perhaps someone can find out why it was an error. Now let's move on to the rest, or to the remaining part of the code. So what this does is creates a static array with a size of info buffer size, which I set very high, 1024, just in case we have a very large host name or very large username, but it could be actually smaller. We can actually change this to 32, for example. If we change, let's see what happens if we change to 16. Perhaps maybe we'll have problems with 8. Let's change it with 8. So what it does, it creates an array of characters. And what we will do is we will call a function getHostName, which is a Unix standard host function, and store that hostname into our variable hostname. And we will be using the same buffer size, 8, so that we do not exceed the number of elements. The same with the username, and then we will print it out. As you can see, we have defined here our first parallel region. So this is the declaration of the directive, pragma omp. And then we have the parallel construct. So what this is instructing the compiler is that to treat this region, which is enclosed into this scope, to treat this region as a parallel region. If and only if the compiler is understanding openmp, which has to be enabled by the flag when we are compiling it. Let's see what happens if we don't enable the flag. We should be able to see this code running sequentially. That means that it will get the hostname, store it into the hostname buffer, and also username variable, and then printing it out. In the second part, we will be using cout to do this. So here we are. As you can see, it actually is telling me that there is only one thread, of course. This 0 here was defined originally in, was defined originally here. Hold on, in our defs, because OMP was not enabled, and that is why we get the 0. If we change here, whatever it is, it's going to be quite curious. Let's see, if we change this, we should be getting, for example, -1. What happens? Just curiosity. There's a question from one of our members of our audience. As you can see, it's showing us as if the thread ID is -1. It's just definition of this function here, which was overloaded by this defined construct. Jose. Yes, it only asks for one thread. Oh no, Jose. I would like to make. So actually, Slurm. It uses a divide of tasks and another division of tasks per cores and tasks per core. So what it is actually doing is assigning the number of tasks that it can. Okay, well, a very good question. No, but Jose, there is no problem. There is no problem with this because it actually is the n is telling is that we will be running one task, and the -c will be telling will be saying the scheduler that we are going to use #1 number of tasks per core. I mean, of cores per task, so they can instantiate the whole number of threads that we will be using. I mean, the whole number. I mean, the total number of cores that we will be needing for the task at hand. The n1 is okay. The uppercase n is also necessary because we're going to use only one node. We don't use openmpi. We don't use MPI or openmp here, so it's actually okay. Okay, so let's move on. Okay, now let's fire this up. Like I said, it should show us only one, but what if we then enable the openmp flag? And we should see a buckload of processes. And yeah, there is a buckload of processes. As you can see, how many processes have I created? 2 cores or 2 threads. And what actually openmp is doing is forking out these 2 threads, and it's reading an environment variable that is called omp num threads and instantiating each of the threads. So what it actually is doing, and this is actually a very important part of it, I don't know if you are realizing this, but it is actually telling that each of the instantiated threads will be executing the same piece of code. Now there are some problems here. Yes, Rafael, it's a very good question. So calling up openmp get num threads is not a very good idea because the threads are not forked. So how can you get the number of threads if you're not inside a parallel region? It's a very interesting question, but think about it. That is why we needed to overload this function call using the definition here in case where openmp flag is not defined by the compiler, which in case this is what we use this definition here over here. Because once the OMP pragma is not recognized, this is executed, this is no longer a parallel region, and this is executed sequentially. So if we will actually eventually call this function using the OMP library, it will actually throw us an error. Okay. But with 16, let's see if it does it with 16. By the way, Carlos, do we have any limitations into the number of cores that we can actually request into this partition?
32, up to 32.
But I suppose that a lot of people are doing tests right now. Okay, so Esteban, to answer your question, yes, we can use OMP num threads. Actually, in the, let me show you, let me access. In the cluster, the script, submit job 2, OMP2. Let's open up with VI. Let me increase the font size. Esteban, if you see this, actually it creates a temporary script, temporary file named .tmp random, just as with the Julia case and the OpenACC case. And inside the script, it actually defines the OMP num threads and synchronizes with Slurm CPUs per task. Okay. So we can overload this. So we can actually overload it, but overloading the function that we are sending here. So this is what I'm trying to do. So if I do this, OMP num threads, and let's call this, oh, I'm sorry. Say this is 2, and let's request from the scheduler 4. It should only fire up 2, but I think we have, I think I submitted or requested too many resources, and I have to wait in the queue. So let me just stop this and restart the kernel, and let's redo it again. There you go. So as you see, I requested 4, but I'm actually only using 2 because I'm overloading the OMP num threads environment library, environment variable. But I haven't reached out that just yet. I mean, there. I just wanted to show everyone what happens or what means to open up a parallel region or to actually do their first attempt of parallelizing something. But there are some things which we need to address right now. Specifically, 3 things. We have a race condition implicit. I don't know if you noticed this. We will shortly discuss what a race condition is. And we also have another problem, which is a flushing problem that stems from C++. Now, generally, cout, it writes to a buffer that depends on the way that it's configured. And the end line flushes the buffer into the cout, so it prints. Each of this, let's say, less hostname, less hostname is an individual call to writing into the buffer, into the cout buffer. So what happens is that when you have multiple threads creating, the cout turns out that it will actually write into that same buffer simultaneously in an asynchronized way. Now, I believe that the cluster is very well configured because it's not the case in the cluster, but I would like to show the case of, oops, I'm not seeing, Jesus Christ, what's going on? Okay. Oops. Sorry. There you go. This is not the case, for example, in my computer, on my computer. Let me show you on my computer what it does. And this will be actually very interesting. Let me erase this part of here. Let's execute it. As you can see, the first part, everything prints ceremoniously, perfectly. Not necessarily in the order that one would expect. My computer has 8 cores. Actually 4 cores and 8 threads using hyperthreading. But when you reach into part 2, what actually happens is that you see then the overlapping of the calls into the cout. This is a major problem with cout, and there are clever solutions to this. One of them is flushing, or flushing is straight 1 and 1. The other solution is to write this output statement into a single output statement, not a multiple output statement. Look at here, we have four calls to cout. Actually 5 calls, the end line flushes and writes as well. So we have a problem where all the threads are writing to actually the same place simultaneously, and there is no order. That is why we get this disorganized output. Okay, this is a very important thing to keep in mind. And this undeterministic behavior is undesirable. This is the reason why from here on I will use printf. I know there are clever solutions to this. And the clever solutions, some of you have them. And if you have them, please comment out in the chat. I would love to implement the solutions. But I honestly prefer printf. So outside of parallel regions, I will use cout, and inside parallel regions, I will use printf, because printf behind it, and also depends on the compiler itself, but printf, what it does, it actually locks to write when it's writing. So if there's another process waiting to write into the cout, into the standard output, then it has to wait until the previous process has done the writing. So it will always be written in an orderly fashion, not necessarily orderly fashion, but it will be written at least one by one. We don't have this kind of buggy behavior. This is what is called a race condition. So we have multiple threads writing into the same place, okay? And this buffer is in memory. And then when it flushes, this buffer is loaded into the standard output in Linux. So the standard output is actually this. Okay, so this is one of the reasons why I would like to invite you to understand the printf statement. If you don't understand the printf statement, please write down into the chat. Now, this first exercise was also to show you something that is implicitly unseen, but it's very important, which is this call that we're doing into the hostname. So hostname is actually a file, is actually a variable. How is this variable declared into the parallel region? We have not discussed that yet. We have only seen that in our view of openmp, what we're doing is we're forking threads to run multiple, let's say, data. In this case, we're executing the same portion of code in all the threads. So we're actually mostly doing this. But if you can see here, we need to take care of the private and shared variables. What is going on behind the scenes is that, I'm sorry. So openmp, for each of the threads, is writing to exactly the same memory location. By default, this variable will be shared. The best way to avoid, for example, race conditions of writing into that same variable is to use, for example, here, or instantiating a private clause to hostname. But then we will have another problem. Does anyone care to dive in and say what the problem will be? For example, if we declare hostname as private. There are two advantages. So hostname is actually a static array. So it's referenced in the stack. So when I recreate this, when I'm forking this parallel region and I'm telling the compiler that this variable hostname is private, it will actually create instances of the variable hostname into the process. But the problem is that the data stored in the hostname cannot be predictive. That depends, for example, on the garbage collection that you have. If you're running, for example, Chrome or heavy thread applications, for example, in my computer, there's a lot of garbage left in the RAM, and sometimes you will see a lot of freaky numbers when you're looking into that. But this will be, for example, a solution to avoid race condition. Let's give it a try. No problem. But we will actually don't see the race condition, don't we? Because we're actually we're writing the same information over and over again. It doesn't matter which thread we're using. So this was redundant, but this is a very important concept that we will look into our next section, where we look deeper into the OpenMPI specification and the library, the functions that we will be able to use. We will look them at a brief overview, and then we will delve into the exercises. So let us change this private hostname and compile again, and rerun. Esteban, I'm sorry, I'm going to erase this overloading of the OMP num threads because I want to use all the 4 threads. As you can see, there is no problem, but there wasn't supposed to be any problem. But I hope that you understand why this was an issue that we need to address. And Alberto says you have to redefine it inside. There are 2 ways to redefine it inside, and we will look into that afterwards. But for the most part, this exercise was to review 2 things. Whenever we are inside a parallel construct, all of these lines will be executed by all of the threads. Okay, so we need to now divide and conquer, which is the next part, which is adding up this construct to a workload, a workforce divider somehow. So we have different kinds of workforce dividers, which are sections, force, and this is what we will be looking at afterwards. There's a question from one of the audience. So why does turning hostname and username into private variables result in garbage sometimes? Don't quite get it. Very good question. What happens when you have a static array defined inside a C++ program, or inside actually a C or C++ program? Actually, since this array is created in the stack, its size is deterministic. So the garbage collection does not have any issues deleting the array, but it will actually be deleted when the program is finished. But when you have, for example, a pointer, well, actually this is a pointer, but when you have, for example, a dynamic array allocation using new, for example, then you inquire into certain problems because then you don't know, the compiler does not know preemptively what will be the size of the array, so they can allocate the space. So there is no way that we can actually do this private allocation itself. So what we will need to do then is perhaps declare them inside the parallel region. If this is going to be a dynamic array, then I would probably define it inside here. For example, hostname X. Inside here.
I also
sorry.
have a question regarding.
Go ahead, Aurelio.
If I don't have first private, every thread is accessing the same variable. So
exactly. Yes.
If I have private, every thread creates a copy of the variable, so that copy is not initialized properly.
Exactly, but this is also compiler specific. I have to say this because every compiler has a different way of. Let me give you a brief example. If we do, for example, here an int I, yes, so the compiler will create an integer variable named I. Well, but does not necessarily mean that it will initiate the portion of the memory where I is stored as zeros. So there are compilers that do this for the user. So they actually do this initially, but there are compilers that don't do that. It's compiler specific. That is why it is sometimes a pain to do this. When you have this kind of problem, the best way to do is, instead of using this declaration of functions or of variables outside of the parallel region, why don't move them inside the parallel region? If we move this function, this variable inside the parallel region, you take care of the problem. Why? Because hostname now is a private variable to each of the threads, as well as username. And this function getHostname will be only writing to its private variable. Why then a question emerges, as you mentioned before, why then is it that we don't have a problem because this function or this variable was declared outside of the parallel region and everybody's writing to the same variable simultaneously? It's because they are writing the same information. So when you're reading or writing, you're reading and writing exactly the same. So there is no actual change into the data. If each of the threads will be writing different, for example, messages, then we will see a race condition problem. okay? Which is actually what usually happens with cout, because cout in itself is a buffer that so each of these calls is writing into a buffer until the buffer is flushed. So it's like, okay, I'm going to keep my buffer turned on and receive a bunch of messages. And then when I flush, I will send those messages to the standard output. Just by the way, so that everyone know, Unix or Linux in general, Unix have two type of standard output or ways of that the program can connect or output information, which is the standard error and the standard output. So you can actually write to the standard output with cout or to the standard error, which is C error, okay? But each of this small hostname, small hostname, small in thread is actually independent calls to the cout. We might think of this as a single call, but it's actually 5 calls. 1, 2, 3, 4, 5. So it's 5 times that it's writing to the buffer, and then the end line flushes at the end. But while it was writing, another thread could have been written as well. You see? So it's kind of a crazy thing, but this is why I like to use printf. I know there are clever ways. There is a clever way that we will look afterwards. So I know that we stopped too much in this problem, but let's look into another more interesting problem, and let's go back to the presentation, okay? Does anybody have more questions? Well, I hope not. Well, I hope you do have questions, but let's save them for later on. So like I said, this was the way that we compiled the first example, the disordered output that we saw in cout, which in the cluster we don't see it. Does anyone have a clue and would like to jump in and explain why this happened? And one thing that is very important that I missed to say is, if we look, for example, at the execution, at the upper, the first lines of the execution, there is the API specification. Now, the version of the compiler in this server is, I think it's 7.3, if I'm not mistaken, which is a very advanced compiler. And its openmp API specification is already 4.5. So we can actually look into the 4.5 reference guide, and let's see what it has to tell us. So if we go here, this is openmp. You can actually, let me copy this down and into the chat so everybody has it. You can open up this link that I just sent to you, and this will show you at least a quick reference guide into the API specification. Since we're using 4.5, let's open up the 4.5. Let me increase the size. And this is like a cheat sheet. So it will show us all the definitions of the directives that we will be passing to the compilers, the clauses to those directives, and the way that they work. Okay. Now, let's continue. So for the second part, what are then the work sharing constructs that we can, or that openmp has taken care of? So openmp has identified that there are mainly 2 work sharing environments. Well, actually 3, which is a 4. So loops are very recurrent in scientific applications. Sections, which was meant to divide into tasks that are not necessarily entangled, where the data is not entangled, so that we can split the tasks independently, and the execution of one does not affect the execution of the other, nor the outputs. For Fortran, there is an interesting construct which is called work share. We will not look into that. And there is another construct which I believe is very interesting, which is the single. We will look into that. Now, along with the work sharing constructs and the declaration of the parallel environment, we have some clauses. So the clauses are actually like customizations that we make to either the parallel construct or to work sharing constructs. And these customizations involve the declaration of private variables, the instantiation or the initialization of those private variables, the collection of results, and if we would like, for example, to print certain things in order. And for that matter, I would like to address a certain concepts which I believe which are very important. So let's look into them one by one. So the first two are private and shared. And I would like to do this along the lines of the OpenMPI like cheat sheet guide, this reference guide, because it's one of the best ways to look into things and what they have. So what I would like you to look is into these two types of clauses, private and shared. So what does private and shared does? So private, when I create a parallel region and I declare private and list a certain, what I can list inside a private is a list of variables. Each of those variables will be created into the threads privately. That means that they will not share any data between the threads, at least in terms of those variables. And the shared construct will be, and the shared clause will define variables that will be shared among the different threads. The problem then is that if I have a shared variable, I have to take care about writing it. Okay, so let us look into the next exercise. Oh, hold on, let us review then essentially the entire picture. So what does it have? And then we will look into each of the exercises. Now, a question that arises that you mentioned, Aurelio, is what happens if I have a private variable, but I would like to initialize it at the same time? But I would like to initialize it to the value that it had before the parallel region was created. Because as you can see, when you create a new variable inside of the thread, you're not aware of the value of that variable. So there is a function, or there is a clause called first private. What it does is that the value that was outside of the parallel region will be placed inside each of the threads. That means that the variable that is inside of the threads is private, but it will be initialized with the same value that it had before the parallel region was instantiated, okay? This is a very important thing. Last private. This last private is, let's say, what happens if you are running your parallel construct and you're running a lot of executions. Sometimes you need to recheck if your execution was okay. And many of the things that you test is you look into the last possible value of a variable at the end of a for loop, for example, to verify if the value was okay. If that value is something, then you know that the test passed. So last private, what it does is that it only creates, it only lives, or it's only available, this clause is only available for loops. And what it does is that the last value of the variable that is declared inside the list of the last private clause will be copied back to the main process so that you can access it. Okay? There is another one which is very important, which is the reduction clause. So the reduction clause, it's a strategy. Well, before the reduction, there is one which is more important, which is the atomic clause. Now, this goes into the problem that we had before of standard output and also reading the host name into the same variable. So what happens if you would like, for example, in this problem here, that this function get host name only writes to host name one at a time. So atomic, or there are several clauses that ensure that this happens. Atomic, what it does is it will tell you that if you, for example, declare an atomic before the get host name, that means that this line will be done one at a time, okay? But atomic is meant for many other things. For example, for reading. In this case, for example, this will be an update. So this atomic is actually meant to update the hostname file, but we would like to do it one thread at a time. Okay. Now there's another one, which is the critical, which is a more simpler version of atomic. So the critical, it will actually tell you, okay, I would like this fragment of this piece of the code to be executed in such a way that only one of them at a time can execute it. So what is the difference between atomic? Well, atomic does not exclude the fact that two threads could be writing to different memory locations simultaneously. But critical actually ensures that only one at a time is writing that portion of the code at a time. So that means that it kind of creates not a race condition, but it creates a queue of processes that will be running the same execution. Okay. Now, reduction is a very important operation because most of the time, for example, if you would like to compute the norm of a vector, or you would like to sum a huge vector, you would need to collect the sums. And in order to collect the sums in an orderly fashion, you need to make sure that everything is written into one variable, for example, or a series of variables in an orderly fashion. And then in the end, you need the sum to be somehow outputted to you. This is where the reduction clause comes in. And to cooperate with the reduction clause, there is also an ordered clause. For example, let's say we would like to have a print statement to be printed in an orderly fashion. For example, we have a loop that is running from 0 to 10, I from 0 to 10, but we would like the print to be not in a disordered way, but it would like to print I will for the first iteration, second iteration, sequentially. That doesn't mean that the computation has to be done sequentially, but the computation could be done parallel, but the printing, for example, will be done in an orderly fashion. That also applies to other kinds of things. And then we have the schedule. So the schedule is a very important clause for the for loop, because the schedule is the divide and conquer strategy that you would like to do. So in my case, I'm not very knowledgeable of the best strategy, so I always use auto. Okay, so you can always use, for example, schedule auto, and it will be actually the best thing that does. So the compiler chooses for you, or you can use runtime that actually kind of specifies, okay, what is the chunk size of the for loop that we have, what is the number of threads, and maybe we can have a best case scenario for divide and conquer. Okay. Now, in order to complement all of this work share and these clauses, we need to have also a manual way to ensure that we are reading and writing memory in an orderly fashion. I already mentioned superficially, but we will look into the exercises, that there are constructs such as critical, such as atomic, such as ordered, such as, I forgot the name of the other one. I think those three, in which a certain region will only be executed by a single thread. But you can have, for example, barriers. What happens when you look into the architecture and you look, okay, so I have that my process is running in a hardware that has two CPUs, two independent CPUs. Now their cache is different, and I'm writing actually the same, two different processes in CPUs, in different CPUs are running into the same, for example, variable. So I use the atomic or the critical construct, critical clause, and then what I'm doing is writing into that same place. But then I would like to synchronize. So we have a problem, that is the information stored in one processor does not necessarily is in the other processor. So there is a level where the memory that's stored in the cache needs to go to the RAM and then actually redeployed back into cache of the processors. So there are memory operations that we can actually, we need to ensure that they are actually synchronized between the workers. So there are two interesting ways to do this, which is creating a flush, OMP flush. So OMP flush, we can actually tell the compiler, I would like to flush the following variable, which was computed or recalculate it over and over again, or we can instantiate a barrier. What is the difference between a flush and a barrier? Well, the barrier in itself, it creates a semaphore so that everybody will be waiting until all the threads have finished their work. But the flush does not necessarily have to wait. The flush is guaranteeing that nobody is touching, for example, that variable. And this is actually very interesting because you can have execution of code. So some worker there could be working on something else, but it's not touching a memory, which I think it's critical. But the flush, what it does, it will actually tell, okay, so let us synchronize this memory among all our worker nodes, or our worker threads. But it will not stop the work of a thread that is not actually colliding, or there's no memory collision. Okay. So there are two ways that we can do that. And like I mentioned before, so the ordered fashion that we can, for example, do certain operations, or critical if we'd like to use, for example, a block that we won't like anyone to access it, or the atomic statement. There are two other statements which are very interesting, which is the single statement and the master statement. We haven't talked about it very much. So the master statement is, I can actually, inside the parallel construct, enforce that certain pieces of code can only be executed by master. Remember that the master is thread 0. And thread 0 is the thread that is spawned from the parent. It's actually the same parent. So in fact, when openmp, or when we're parallelizing and forking threads, we are only forking n-1 processes. Okay, this is actually very important. But we will look into an example of master, which is actually critical, because when we spawn all of these threads, certain variables, even in the master thread, are private, even though it was actually inherited. It doesn't inherit the same variables as the parent process, and this is actually very crucial. And the other construct is OMP single. OMP single, different from master, tells I would like this part of this portion of the code inside a parallel construct to be executed by any thread. So any thread that is available. Let's suppose that master is busy. So thread 1 or thread 2 or thread 7 could take care of that portion of the code. The advantage between master and single is that single, then it looks into who's available and it runs the portion of the code, and it actually does not have to wait for the other one to code. The master has an implicit barrier placed at the end of the region. We will look into that. And then at the end, we have tasks, which will be an interesting way to solve the problem of Fibonacci and palindromes, by the way. Okay. Along with these directives, that if you look into that, there are directives that go straight to the compiler. Up to now, we haven't done anything, I mean, library-wise. OpenMP has a library that we can actually use it. And here I will have displayed certain routines, which are very interesting. One of them is OMP get num threads that we already seen in the example before. And OMP get num threads shows you the threads that you have available. OMP get num devices, this was actually implemented, if I'm not mistaken, in 4.0, in which OpenMP is now able to share work into different architectures. So it shows the devices that are available. This other function is a way to set the maximum number of threads. You can either set it by the environment variable, which is OMP num threads, or you can set it using, for example, set max threads. This also set max threads is crucial when you have nested parallelism. And we will discuss that when we reach into Fibonacci. This is actually the way that we can enable nested parallelism using true and see if we have nested parallelism enabled or not. This is one of the functions that we can use outside of the parallel construct, the same as set nested and get nested. it will tell us if we are or not inside a parallel region. Just to answer one of the questions that you had before, that you cannot use get num threads outside of the parallel region because it doesn't make any sense. Well, perhaps you can, but it doesn't make any sense because you don't have any threads. Okay, so let's review if you have some questions because we are all ready to delve into other problems. Okay, very good question, Alberto Mario. So in order, they still have to wait for each other. So let us look into the diagram because everything, I mean, I know this is a bunch of mumbo jumbo, but let's look into one diagram. So let's, for example, think of that we are forking the threads and we're processing the routine one and we are splitting the data into this portion of here, okay? Look that I did not, I mean, intentionally or purposely, I draw that it was data 2, data 1, data 0. It doesn't mean that the data is split, like this first chunk goes to the first thread, second chunk goes to the second thread, and third chunk goes to the third thread. Actually, depends on who's available actually after instantiating and executing the code. So let's say, for example, at the end of routine 1, I need to print something. So I need to print the status of how things are going. So if I would like to print in an orderly fashion, it will look into the work sharing construct that I had. If I had a for, then for example, for I from 0 until I equals n minus 1. So if I have a print, it will actually show the print of I equals 0. So let's suppose that the routine one is computes the fors and then prints something. So what it does is all the processes will be computing the fors, but then when it reaches the print, it will only print the one corresponding to I equals 0. So everybody will be waiting until that print is done and then print 1 and then print 2. But once print 0 is done, it will proceed to the next calculation. So somehow it's like, okay, let me print, but does not necessarily mean that it has to be thread 0 that is going to print the first element. It could be, for example, thread 1. But what it does is that if I'm done printing, then I can proceed with the next calculation. So it's somehow like imagine it like a stepwise, like going up the ladder. So you go one step at a time. But if everyone is trying to advance one step, once you advance your step, you keep going until you advance into the second step, etc., etc., etc. So it's a very beautiful strategy, but it has its drawbacks. The beautiful strategy is when you like to check that things are going very well, but it's not necessarily the most efficient way to distribute a workload. Now, there is another thing that I would like to show you here, which is a scenario that frequently occurs, is that you have two potential routines that could be parallelized. And then you parallelize the first region, for example, routine 1, and then you join your forks, you run something or nothing, and then you recreate or you fork again your threads. What happens here is that either you're changing a strategy of parallelism, but you're actually creating a bottleneck because you're joining threads and then forking them again. This is not a very good practice. So what usually we should do is we should join the two routines in such a way that we can actually split the entire computation. So this, for example, is a strategy of divide and conquer in the data. So we have split data among the first routine, but we have in somehow implemented that the routine 2 will be continued to be executed inside the parallel region. See? Okay. Now there are strategies. Now there's something that we need to discuss before we proceed. The problem is, imagine that in order to execute routine 2, you need necessarily the output of routine 1. Okay, so there are ways to do it. We can implement a barrier so that if all the processes have not finished with routine 1, well, while you're ending, you have to wait. And then you place a barrier here. So you don't let anyone pass until everybody reaches this state and then advance to routine 2. But if your routine 2 has nothing to do with routine 1 and still splitwise is a lot of data, then you don't need to place a barrier. You just let them through, okay? Now, there is another special thing that could happen is, imagine that...
Sorry for interrupting you.
We're going to break?
Yes. Can we take a 15 minutes break?
Yes, we can take a... I'm sorry, I didn't see the chat.
Yeah.
Okay, let's take a 15-minute break.
Yes.
See you back in a while.
Some questions?
If you have any more questions, I will be here.
Yes. So see you at 3:45?
Yes, let's see each other at 3:45. We're only missing a little bit, but let's go for it.
barriendo. Okay, the time is over, so we can continue with the workshop.
Okay,
Well,
Aurelio, thank you very much.
we have a couple of questions.
Yes, we have a couple of questions. So there was one question about the hyperthreading. So hyperthreading, Intel's technology, what it does is exposes two contexts to the kernel per processor. This is done in a way that you can exploit high levels of throughput because most of the applications are not actually, well, most of the older applications were not heavily threaded. But the problem is that when you are so there are two sides of this. So one of the things is that the kernel, what it does, it exposes to a process a context so it can use resources from the CPU. And it does it in a way that every process receives a fair share of the CPU workload. But when you enable hyperthreading, you are actually telling the kernel, okay, there are two contexts that I have available. So what the kernel does is it actually ships the workload into the processor, and lets the processor takes care of who goes in. So actually what Intel was doing was exploiting some kind of concurrency in its own physical processor. So making the downtime of certain certain processes available to other processes so that the processor is somehow available, and at hardware level is done much faster. So in one way, you get a lot of throughput if you have multiple applications that you're not using, for example, heavily. But I have to say this is a very bad idea, for example, for databases, because then what you create is you create what is called a thread storm, that there are so many processes that are occurring that the processor needs to find a way of dealing with all the workload. And what it does, it actually increases the time to execution. Okay, it might execute quite fast portions of the code, but increases the time between executions, in between consecutive executions, and the time that you get resources available. It also has another drawback. It's with NUMA capable devices. When you have, for example, two physical CPUs in a motherboard, there's an interesting thing that happens is that memory is somehow distributed in a way that it's closer to certain CPUs. So for example, assignment of memory location is generally driven by what processor is assigned to what process. And when you enable hyperthreading, you miss this, you lose this. So if you want, for example, high disponibility, like with databases, then that's a huge drawback. So I would recommend with database servers, never turn hyperthreading on. For HPC, never, because you have intensive and highly threaded applications. So they will make the most out of every bit of the CPU. And if you enable hyperthreading, what you are creating is somehow like a storm of processes competing for resources. Although it's done at the hardware level because the kernel does no longer have to worry about this, but somehow it's not as efficient. But if you would like, for example, high throughput, it's a very good idea. For example, for desktops. Okay, so this is the principle behind hyperthreading. AMD recently incorporated also hyperthreading into the SMBs into their architecture, their new architecture, their Reason architecture. But generally, for heavy loads, HPC databases, it's not such a very good idea. Sometimes it could be a good idea if you have an Apache server, not Apache server that has not so high concurrency. But if you have, for example, a heavily loaded Apache server, never turn hyperthreading. It's a bad idea. You will get a lot of downtime for your clients. Yes, yes. So, yes. So this is a comment on what Esteban is saying. So that is why AMD and the new AMD chips are actually very good for HPC. Actually, there is one chip that has 88 physical cores embedded into it. It's awesome. It's kind of the fastest CPU on earth, but it's almost $8,800 each die, each chip. So so we need to spend a lot. And even though, and like Esteban is saying, it's cheaper than Intel. If you look at Intel's best performing server, is about $200 or $300 more expensive than the best of the best right now from AMD, which is actually it. I think it's embarrassing for Intel. I'm sorry if there is anyone that loves Intel here in the audience, but AMD just smacked Intel hard. But anyway, let's move with our. Okay, hold on. Hyperthreading is better for CPU intensity, such as numerical applications. No, if you would like to have throughput, if you have, for example, have multiple processes that have, for example, a lot of downtimes. So that is why, for example, my personal computer, it's perfect for hyperthreading. I'm not using all the time all the CPUs, but if I'm, for example, doing a heavy simulation, I would disable hyperthreading, because then Google Chrome will be interfering with with whatever calculation I'm doing, and then what I get is like cheap performance increases that are not big idea, are not the best idea. And the other problem that you get is this threading storm, which increases. So let's say, for example, a delta T time is the time that you require to make a switch of context for one process. When you have a lot of threads, and when the number of processes matches the number of threads, of pure cores, then you will only see like a decrease in performance when you're capping about 85, 88% of the usage. But when you enable hyperthreading, I say, for example, I have 4 pure cores, but I have actually 8 like virtual cores or context cores. Then I have, for example, 7 applications open. So actually the cores are struggling to assign priorities to the process. So I don't feel it really that much, but in HPC you will feel it. In databases you will feel it. You will feel it, for example, when you load up Google. Google loads up perfectly your email service, for example. This is very important. Yeah, like Esteban is saying, it's better to disable HT. Much better. And also think about it this way. The idea of the context is to provide, is the hardware telling the kernel, look, I'm closer to the algorithmic logic unit, and I'm closer to the registries. I can actually do things faster than the time that you need to communicate to me that you are changing the context of a process. I can do that much faster. So you have a performance increase, which is actually very good, but it's actually very good for desktop environments, not for server environments. It's a very, very bad idea. And NUMA, for example, you're losing a lot of high performance memory access, for example, with NUMA, because hyperthreading, you lose NUMA entirely. Okay, so I hope that actually raises the question. It's perfect for your desktop, never for a server in a production environment. Okay. Let's move on. The only 2 slides that I wanted to show before, the last 2 slides, were the ones that I was mentioning about the special routines where you need them to be executed sequentially and can be done either by a master or by a single routine. Now, remember that the master, I mentioned that the master has implicit barriers. It means that if, for example, I fork the threads, my process, and then I have the routine 1, which is executed parallel-wise. And then I have a master section. There are two barriers which are implicit in the master section. One barrier is that it will wait until everyone finishes routine 1, and then we will execute the master section, and then everybody has to wait until the master section is finished in order to proceed to routine 2. This is why this is why the single construct was built, because then you don't have to wait for barriers. You can actually take away all the barriers and just let your processes advance from routine 1 to routine 2, as long as routine X is not required for routine 2, okay? This is a very important fact. And you will have, and you will use the clause wait. I mean, no wait. The clause no wait will just allow barriers to be removed. Okay, so let's get down to business. So the second exercise is actually this difference between master and single, and I wanted to show you. So let us look at really quickly. So we have two parallel regions. So one parallel region, which is actually inherited from our first exercise, which actually shows which thread is executing what. And what I'd have in the middle of this parallel region is a sleep. And the sleep is corresponding to the number, to the ID of the thread. So if I compile this and execute this code, I should expect to happen in the first portion is that thread 0 evidently prints first, because of course its sleep time is only 0. Then thread 1, then thread 2, then thread 3. If I'm requesting, I'm only requesting one thread. I'm sorry, hold on. 4, there you go. Oh, it's not turned on. What happened? Okay, I'm sorry, I'm missing something. I think I'm missing something. Did I miss something? Oh, this is a slurm. I'm sorry. So we're getting the output not necessarily in the sequential order. Oh, let's do it in my computer. So let's compile and run with openmp the second exercise as is. Master single. And what you can see is thread 0 is the first one to go out. Thread 1, thread 2, thread 3. In this case, I have 8 threads due to hyperthreading, unfortunately. And then in the second part, try to guess what happens in the second part. So if you look into the second part, it actually prints, and this print is done inside the OMP master. So we have declared here a region OMP master. So everybody has to wait until this actually is executed. So we're inside the block thread ID. And now what we are doing is we're adding the sleep time 1. And then after that, we are saying that the extra time is 1 second. And what happens when we are doing the sleep time? It will actually do something very weird. Does anybody know or care to try to understand what is going on? Try to do it yourself several times. Let's do it in the server so that you can check it out multiple times. So the first part is written sequentially, like in an orderly fashion, but the second part is not written sequentially in an orderly fashion. What is going on? If we look at the code, so we create an integer variable, which is the ID of the thread. Then we initiate the master section. So this is only executed by master, and we define an extra time. Look, that extra time is equal to 0. OpenMP parallel, remember that we stated that by default, variables are shared. So we can, for example, say this shared extra time. It's actually implicit in the declaration. So every thread has access to extra time, but who's writing extra time? Only master, right? So what's going on here? So each thread is running a sleep that is corresponding to its ID plus the extra time. But we have a problem. Some threads are somehow appearing before thread 0, for example. So what we should expect is that thread 0, 1, 2, 3, 4, 5, 6, and 7 will appear accordingly. Why isn't that the case? Does anybody care to try to guess why? So there is an interesting view of it. Yes. So because master was executing the code, what happens to the remaining threads? What are they doing? What are the threads doing in the meantime while master is executing the code?
They are sleeping.
Are you sure?
Not.
Why not? Or yes or not? I would like you to play with this. Let's change it to single. What we should expect that will occur. Let me just turn off this first parallel region, which is not necessarily, not necessary. Let us compile it again. Let us execute it again. That's much faster. Da, 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 da. Now it executed just on time. Let's change back to master, okay? So actually it entered into thread 0, so this was the master was executing. But doesn't have to be that way, isn't it? Let's run it again. See if it's master that executes it or it's somebody else. And let me change the times here because sometimes this 0.1 might be too much. Let's say 0.2 and let's say 0.20 here as well. 0.5, so let's like penalize them like 1 second. Let's see what happens. Compile and execute. Huh. So it seems like with the single construct, we get the desired output, don't we? But with the mastered output, with the master construct, we don't get the desired output. Then what is going on? What is going on is it has to do with the weight. Let's execute this again with master. Let's see that the output does not necessarily have to be ordered. Look, first 1, then 0, then 2, then 3. So what it means is that with master, everybody just simply skips and doesn't wait. Is this the desired behavior that we would like to have? Depends. If the variable extra time is needed for the next portion of the execution, we wouldn't like to have this behavior. But we can enforce this with a single construct. So conversely, other than the master construct, the single construct has an implicit barrier. So that everybody has to wait until the single ends execution, unless we use the no wait clause. Remember that I showed you the reference guide. So we can go into the OMP single construct. So OMP single is right over here. And it tells us, so we have a no wait clause. So no wait clause is simply, it's telling the compiler to compile this so that anybody can execute this, but the rest just don't have to wait for it. What will be the ideal scenario in which this happens, in which the execution of this portion of the code does not imply any, or does not affect any behavior of the other threads, like in this case. Let's try with the no wait and see what happens. We should be getting the same result as with the master. Okay, so in this case, our solution to the problem was using the single without the no wait clause. As you can see, again, we have the same behavior. So the thread 1 entered first, and then this thread 0, then thread 2, then thread 3. Okay. After thread 0, all of them appear in sequential order, which is the desired output. But does not necessarily mean that this is the behavior that we would like to have. Is there another way that we can enforce, for example, using the master clause? Remember that I also mentioned that we have ways to enforce barriers. So there are two clauses, there are two, not constructs, but there are two like directives that we can use to enforce this behavior, which p flush. Okay, so what I can do here is let us try and do an OMP barrier. Pragma OMP barrier. So what will happen is that the threads will have necessarily to wait until the execution of the master, and then they will call extra time. So the barrier has an implicit flush. Remember that the flush was our assertion that it's all the memory is coherent among all the threads. That means all the threads are accessing the same shared memory. And it's not like corrupted in any way. Okay. Let us execute this right now and see what happens. Oh, sorry, right here. We'll move to the next exercise. There you go, 0, 1, 2, 3, which is the desired output. Now, try it by yourself. What happens if you place, for example, here a flush? Let's look into the reference guide. So the flush statement, we have to use, and in parentheses, we will have to place, for example, the variable that we would like to make coherent, or so that the value is updated to all threads. I don't see to all actually CPUs. Hold on, where is the flush? Flush. Oh, there it is, the flush. So you can use flush with or without the list. If you use flush without the list, what happens is that automatically all the shared variables will be synchronized. But if you use a list, then it will automatically use only one. It will just guarantee that extra time is a desired value that it should have at this stage. Let's check it out. Anybody has any questions? I'm moving too fast, or is it okay? Yeah, so the flush didn't work. Then again, what happened? Well, this is one of the undesirable behaviors of master. So there is no barrier. That means that the threads will continue execution. But the continue execution means that if a thread reached this place, or all the threads except, for example, master reached this place, the problem is that extra time might as well have not been ready for being written at this stage. So whatever thread is actually updating or entering, whatever master is doing, he might be caught up in the sleep. And therefore, this extra time is not yet updated. So the flush is already flushing when extra time is equal to 0. So this is actually like a bad behavior. So there is another way to also work this out behind the, besides the ordered. Does anybody care to jump in and try to guess what can we use to, to enforce, for example, that all are synchronized? That extra time is synchronized to all of the threads? Well, think about it and let's proceed. So we have already discussed something about static vectors. One thing that I would like you to do is to open up one exercise that is called X2 vector. And let's look into that. If you have more questions, please raise your hands. So this is actually one of the most interesting examples that I like, which is the behavior of pointers. Like I mentioned before, this, for example, is a static vector. It's defined with 8. I purposely defined it with 8, dimension 8, and I made it private intentionally. So what I did is I enclosed this region into critical region so that inside this block, each thread is made, each of these statements is run only once. But let me just turn this off so that I can show you this behavior. It's a very interesting behavior. See what happens. So what I'm doing is I'm firing up my parallel region, and then I'm printing inside the block. We already know that there will be unnecessary race condition, but this will be printed in a disorderly fashion. We can enforce an ordered printing using pragma OMP ordered. We will look at that later with a for loop. It's much easier. And what it does, it will update, or it will actually go into the item TID, well, modulo 8, because we wouldn't want to pass over, and assign the value of 100. This is meant if we have, for example, more than 8 threads. If you're firing up openmp, let's say for 16 threads, so thread ID 15 is trying to write into the vector's 15th position, so it won't find any place. It will throw a segmentation fault. So this is why I'm using the modulo here, so that it will always go into a slot in the vector. And since the vector is private, let's see what happens. Now we have a sleep here, so let's place a 0.1. I don't care about this. And then one thing important, look that we are C-outing into this, okay? Let's leave it with 1. That's okay. Uh-oh, hold on. I missed to change the name, vector. Cut it down. There we go. Oh, remember the race condition that we had that I mentioned to you with cout, a very undesirable behavior? So we need to fix this. So we're going to print. This is why cout, I don't like it very much. I'm sorry for those lovers. Cout lovers. Okay, now we need to place a specifier. So this is an integer. So the specifier for integer is %d. And then this actually is print value here. I'm missing a parenthesis here. Am I missing something else? Yes, enclosing, and this is printf. We'll see something peculiar that I would like to show you. What do you think is going to happen? The same behavior. Why?
Because only the statement is acknowledged, not the full block.
Exactly. Very good observation. So we have simultaneous prints. So each of these prints is done in a secure fashion. But since we have each of these prints, then we have a problem. This place here is not run in an orderly fashion. So we need this to be run by exactly only one of the threads. This is why I use the OMP critical. Okay. So let us re-enable OMP critical. We have defined a critical region. And in this critical region, then this portion of the code is only executed once, every thread one at a time. Okay, now let's run again. And let's run again. And now we should be able to see the results. Okay. So we are inside the block of thread 0. So apparently the first thread that instantiated or that initially entered the critical region was thread 0. As you can see, thread 1, thread 2, and thread 3 will not be doing anything unless thread 0 is done with the work. Oh, yes, Raphael, very good question, very good observation. In the first example I mentioned, that cout, you can actually do the printing then the flushing simultaneously. Not simultaneous, but you can actually load into the buffer a single string and with only one call to cout. In this case, you can do it the same, but it actually complicates things a little bit. But I wanted to show why the critical region was important. Okay, but I also wanted to show something very important, which is instantiation. It has to do with Aurelio's question before. If you look at instantiation, not all values were instantiated at zeros. Thread 0, if by any means this was supposed to be working in an ideal way, then variable v, since it was private, what I would like to do is that all of these values will be somehow inherited into the region. Is that possible? Well, so far what it did was actually creating static vectors of the same dimension inside each of these threads, but the assignment is not exactly the same assignment as the original variable v. Now, the problem with the assignment is that it's not even zeros. We have numbers which are very crazy here. These numbers are simply numbers left behind in the memory and access to this, like random bits or bits that were left behind. But you can see the 100 is actually copied in the proper locations, okay, corresponding to the 4. Another thing, I intentionally printed out the result of the original vector after the parallel region ended for one reason, to show you something. Once we have created our parallel construct and we have declared the variable v private, not even master has access to this variable again, okay? It only has access to the variable that it's inside inside the parallel region, which is a private variable, and its values are never, and the values of this variable are not corrupted. Actually, they're unchanged. This is a very important behavior. But if we would like to, for example, copy these values inside the parallel region so that each thread has an identical copy of this, and then after the end of the execution, I would like to retain part of this information and bring it back to V, then how do I do that? This is where we have two clauses which are very important, which is first private and last private. So what does first private do? So first private will actually create the variable v and copy the data to the variable b if there is a copy associated to the variable. Now the question is, do you think there will be a copy for this array here, even if it's a static array? Does anyone care to jump in? So let's try to make it. So copy private. What we should expect is that v is private and we're copying the values of v outside or before the parallel region into each of these. What do you think will occur? Let's compile and run. Or try it yourselves in the meantime. Oh, sorry. Yeah. Yes, we have a problem with copy private. Let me see the reference. Parallel region apparently does not accept copy private. It's first private, not copy private. I'm sorry, this does not exist. It's first private. First private, first private. Sorry, this was my bad, my mistake. Now let's run. So first private, not copy private. I'm sorry. What do you think happened? Is it the desired output that we wanted? So let's check. So thread 0 should modify the element 0 of the vector. Perfect, done. Thread 3 should modify the third element. So 0, 1, 2, and 3. Perfect. And thread 1, what do we learn? So openmp is smart enough to know that if we have already created a static array, even that v is a pointer, technically speaking, it has a predefined size and it can actually do the copy. So it copies the entire array into each of the threads. And then, just as we mentioned before, once we quit the parallel region, v is untouched because we have not progressively moved or let's say updated v from outside of the parallel region. Questions up to this point? If you generate a string and then print it, would it work? Yes, I was mentioning. Yes, Rafael. I already answered that question, I'm sorry. So what do you think we need to do then to ensure that, well, we can do, let me do one thing. This critical region, we can actually move it further. It doesn't have to be this one, does it? Let's take this sleep away and let's place it actually here. What we need is, I'm sorry. What we need is, the printing is done in an orderly fashion, but actually the, like the, not the instantiation, but the initialization or copying of that, or the assignment operation can be done because v is private. What happens is, for example, v is shared. We will have a problem. When will we have a problem? Remember that we're using modulo here. So if we have a great number of threads, say 16 threads, so the first 8 threads will be writing to 0, 1, 2, 3, 4, 5, 6, and 7. But thread number 8 will be writing again back to 0. So we will have 2 threads that will be writing simultaneously, or we don't know, into that same operation. And imagine if this value 100 is dependent on the thread. So we will have a race condition here, and we will then have to use a critical or another construct that will ensure that the memory is coherent. Okay, so beware with it. So first, private. Okay, so one question. Remember I mentioned that there was a way that we can copy the output or a variable that was private inside a parallel region outside of the parallel region. How can we do that? And I mentioned last private, for example, as a resource, but I mentioned a caveat. Last private is one of those clauses that only exists for for loops. Is there another way that you can think of that we can, for example, have a value evaluated inside the parallel region that can survive even after this region? And I don't know, maybe even modify this array V. So think about it, okay? While we proceed to the next exercise. Right now, let's go to exercise number 3. But we have reviewed certain concepts about exercise number 3. We talked about copying, and we talked about the merit of keeping track of instantiation inside the parallel region. So in this exercise, what I would like you to do is, how do I, in other words, what I would like you to do is think of X as a variable that we have created right here, okay? It's outside. And now what we would like to do is, we would like to see what is the value of X inside the parallel region, but we would like to update the value of X. So in order to update the value of X, we have to be thinking of a clever strategy. So what we would like to do is, maybe we would like to add to X each thread into a very specific value and see what the output will be. So let's compile and run and see what's going on. I am trying to add up here. Okay, hold on. Oh, I'm sorry. This exercise, what I wanted to show was practically the same thing that I showed in the previous exercise, but only is that the definition, instantiation happens exactly with the same variable. And there is also a problem inherited from this related to a question that Aurelio mentioned before. So let us compile and run before that. Because I want this exercise is actually very interesting. Okay. Let's go back. So we have a warning for the first time. This warning is related to X is used uninitialized in this function. If we look at the line number, line 29, line 29 is referencing where I created X. But if you could look into the definition of the parallel region, what I did is I actually assigned X as a private variable. But what's going on? I'm printing the value of X. Check it out. It's right here. But this value of X is private. So remember, whenever we have a private variable inside a parallel, or declared inside a parallel region, or in the declaration of a parallel region, this private variable is initialized, instantiated, but not initialized. Okay. The fact that it is not initialized is the origin of the error that we are getting. So this private variable X here is not initialized with a value. In order to initialize it, either we will have to enter here, for example, say X equals 5. Okay. Yeah. And then compile, and that error will disappear. Let's see. Again, we don't have any errors, and voila. And again, remember that this private variable, its value is 5. We can use actually the same variable name, which is actually awesome. OpenMP is very powerful. Well, actually the compiler. And then it preserves the same value as before. Oh, thank you very much, Jose Antonio. There are many things that need to be improved in the presentation. Okay, So let's move to the next exercise. So the fourth exercise is what I was mentioning to you about the race condition. So let us look into this. So we open up a parallel region. We create an ID corresponding to thread num, and then we're updating the variable. Remember that default behavior is this X will be a shared variable. So that everybody will be trying to write to X. So how can we do this in such a way that it doesn't interfere? So let's see what happens. So if this were to be run properly, we would like that X is updated by 5 by each of the parallel threads. So if it's 4 threads, that means 20. That means that the desired output of X will be 30. Let's see what the output is. Oh, I'm sorry. I need to update, forgot to update exercise 4, shared. Again, I always miss this. Voila. This run actually very well. Let's see if it runs again. Oh, actually, it's running very well. This is amazing. Probably this server doesn't have hyperthreading on, and it's killing my mojo. But and by the way, Carlos, is this? I hope the server doesn't have hyperthreading on.
I guess not. No, yeah, it's not enabled. Yeah.
Okay, because when it doesn't have hyperthreading, some things occur more smoothly than others. But let's run it in my computer where hyperthreading is enabled, and you will see the disaster that it is. Well, we have 8 threads. And as you can see, the 8 threads, so 8 times 5 is 40 plus 10, we should be getting a value of 50. Not the desired output. We got the desired output luckily now, but then again now. So we have a problem with reproducibility. So the origin of the problem here is the fact that everybody's trying to write to X simultaneously. Since server doesn't have hyperthreading on, probably this variable is in cache and it's doing the lock automatically before updating. So there is no need for synchronization. So in order to ensure that this is actually done in an adequate fashion, there are 3 ways that we can do it. One of them is declare a critical region. And once we declare the critical region, I'm sorry for this, I prefer to put it here. We're ensuring that each and only one of them is running. Let me do this change in my computer and so that we can, in fact, proceed as desired. So found pragma OMP critical. We open up the region and X plus equals 5. And let's see what happens here. Let's see if it solves the issue. Oh, voila, there we go. Doesn't matter how many times I execute the code, it will always give me 50. But there's a downside. The downside is that if, for instance, I have had other computations afterwards, there will be an implicit barrier here. And the other barrier, the other implicit barrier is, imagine if I'm updating, for example, 2 variables, or updating actually an array in different locations. So this OMP critical is actually a barrier for all threads. So there is a clever solution for this, which is atomic. And the beauty of atomic is it was meant originally as a construct that only applied to the following line, but it has evolved into being something that actually applies to a scoped region, which is inside these brackets. And you can actually refer to atomic, okay, what kind of operation am I doing, so that Atomic is being careful of the operations that we're doing. In this case, we have 4 operations. Atomic has update, read and write, and capture. So capture, we're not going to discuss it. Perhaps you can Google it, but update is the simplest. In this case, for example, is we are updating the value of X using X. So it's a read and write operation. So we read X, and then we add 5, and then we update X, and then we write X. So this update, so Atomic knows that this update is an operation of read and write. So it makes sure that nobody is reading or writing to X. If this were to be like a write operation, and we don't need to read X, then other performances will take place. Perhaps it will matter if anybody else is writing to another variable. Okay, so let's say update, and let's compile. Okay, where is? Hold on. Primary expression 36. I have a problem. Atomic update. What is wrong with this expression? Is it only taking the next one? Oh, what kind of version do I have? I have 4.5. I thought Atomic, Jose, am I wrong, or Atomic accepts scopes? Should accept the scopes. No, it's not accepting the scope in my case. Too bad. So Atomic only accepts 1 line, apparently, in my case. It should accept more than that. In this case, this is a much faster solution. For example, if you have gigantic matrices or vectors and you're writing to all of them simultaneously. Okay.
I think you can oh, sorry, you can put the scopes if
Thank you for jumping in.
make a block. If you make a block. But
yeah, I made a block.
You made a block?
Yeah.
But a block like critical.
Critical, sorry. Yeah, that's it. It's not called atomic, but critical. Thank you. Thank you. Yeah, that's it. You have to call
it we tried with critical, but I thought Atomic also accepted.
No,
accepted right now
this,
scopes.
This is because
Maybe,
critical takes several. I mean, atomic deals with a single variable, single space in memory. Yeah, so it checks whether this memory is being accessed by more than one process thread at a time. Just a single memory space.
But I think this was before, Carlos. I think this was a while ago. Things change so fast, because I know that Atomic was meant for one memory location and operation.
Yeah, because
but
it
I'm
uses
not
a mutex
sure about
variable.
the new.
I mean, you use a mutex
Yes.
variable for that, so that's what's behind there.
It's still using it.
I would guess. Yes.
My bad. Well, but again, Atomic is the solution for this, and I'm using the update clause for the Atomic. Or critical. Atomic is more efficient, like Carlos was mentioning, and definitely this will throw an error. So let's skip this up. File and run.
I find the difference between critical and atomic. The critical construct restricts the execution of the associated block to a single thread, while the atomic ensures that the updates are atomic. So only one thread can update the variable at a time.
Exactly. So it looks for the memory where the variables is stored and ensures that no other thread is updating or writing or reading, unless, and this is a performance advantage, because if you have multiple memory locations and you're running the same portion of the code, it actually runs faster.
Yeah, because it's non-blocking. I mean, atomic is blocking, so that will cost you. Yeah.
Yeah, exactly. So let's go on to the next exercise quickly. I would like to go into, let's skip into the loop because the loop is the most interesting, and maybe we can go to the Fibonacci just to wrap up things up because things will take a lot of time. Okay. Yeah, so this is actually the most interesting part of what I wanted to show you today. So one of them is we're going to skip this part of declaring random variables or instantiating random variables in C++ using random device, which is a library called random. It's very neat. But what I did is I created two distributions, a uniform distribution and a normal distribution, and I created a type def float decimal. So what I did is I created a couple of vectors or a vector v1, and then I filled it with random number or random noise. And then what I want you to do in this case is use a parallel construct. Well, first of all, create another vector, v2, of the same size, same dimension, and then add two of the vectors. Okay, so I hope that you're trying this by yourselves. So let's go ahead and do this. Let's first run this and see what happens. In my case, I will try to use this as, I will run this, and I wanted to show you also that I created, that I provided you in the defs with a simple timer class that actually begins, that it actually helps to compute the time that has passed between the start and the stop, and then prints a very neat thing. So let's execute this thing. I'm always sorry for the delay. Explaining openmp, it's way too much for only a short amount of time. So if you look at this one, for example, it told me that the random field took 3.3 milliseconds, actually very fast. But this is actually a very small vector. We can actually have larger vectors. The problem is, and before you try to increase the size, think about that this is a static vector. So it will make a stack very large. But although, let's give it a try with 1,000,000. Let's see if we get some hiccups. We haven't done anything parallel up to now. It will be the next phase. So now we're talking, so 0.145 milliseconds. And also the reason is because computing random variables is quite more expensive than computing or other types of random variables like uniform in -1 and 1. So let's proceed with the exercise. So first we need to create another vector. So let's call it v2. And let's define it with the same size so that we can add two vectors. And the next instruction is let's fill it with uniform data. So we will copy and paste this, and let's fill this up with uniform data. And we will use either one of the two generators, whichever you please. You can use Gen 1 or Gen 2. The beauty of C++ provides full stack of variables and options to do things. Okay, now let's compile and print and see if everything is going fine. We have that variable v1 and v2 are set, but they are not being used, which is expected because we are just initializing and assigning, but we are not using the variables, in fact. As you can see, random field is much more expensive than uniform field, but not too much, only 3 times much more expensive. So the next phase is let's do some parallel computation. So I need to sum of these two vectors. So what I need to do is I need to run over this loop and add in these two vectors. Say v1 and v2. What am I doing here is I'm adding v1 and v2 into v1 into v2. How can we parallelize this in an efficient way? But allow me to do one thing. Let's create another vector like result so that we don't have to modify our original vectors v1 and v2. So v1 is a vector of random noise and v2 is a vector of, it's still random, but it's not necessarily noise. It could be simply a uniform distribution minus 1 to 1. So what we would expect is that the res will be updated one by one. How can we do this in a very fast fashion? So let's fire up our parallel construct. So pragma OMP parallel. One thing that I would like to do, if you allow me to, let's take this variable outside and let's place it outside. Let's also initialize it simultaneously. And from this, for this parallel region, I'm going to need k equals 0, etc., etc. So if I do this, what will happen is that all of these threads will be doing this for loop. But the problem is that they will be all executing that loop, the entire loop. But I need to split the work share, the workload. So what I will do is I will fire up a pragma OMP and declare the for construct. In the for construct, I will implicitly notice that the parallel definition implicitly has defined v1, v2, and res as shared. But let's do it manually. It's always good practice to make sure that you know which variables are private, which variables are going to be declared as shared. So in this case, for example, I will fire up this pragma OMP4, and what we'll do is we will split the workload into all the nodes, into all the threads. Will I have race conditions? In this case, we don't have race conditions because, as you can see, there is no we're not writing into the same site at any given iteration of this loop. So we can actually speed this up quite fast. There are two ways that I can do this. And I can show you is we can use a different strategy for the schedule. I do not necessarily, I usually do not meddle with this, but when using for and you're using, for example, the scheduler, I always set it to auto or to define at runtime, okay? And what you need to do is to specify it in a list format. So in this case, the schedule will be runtime, okay? Let's leave it at auto. You can change it to whatever you want and see, for example, performance differences. In order to verify that things are running smoothly, let's also create, or let's also use our timer to see what is the time spent for each of these computations. And let's see if we get a time increase. So in order to do this, let me be a little bit, we're going to try two tests. So the first test is we're going to run this in sequential form by disabling the FOMP flag, and then we will write it in parallel form, okay? So let's erase this. Run it, okay, iterate, okay, yes, because I changed the variable name, so it's J. It's J, J, J. Sorry, bad habit. Okay, warning, 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 ignoring pragma open 4. Yes, so look at this, is a warning because we're ignoring the pragmas. And the rest is set, but it's not used. Yes, so in this case, for example, happens the same thing as before. So the rest is just being assigned, but it's not being used anywhere. So that is why I'm getting this warning, but it's okay. We can execute this. Okay. We have segmentation fault. I'm sorry. This is the worst error that you can get. Okay, what is going on here? I'm copying outside of the region. Just 1 second.
The iteration variable is private.
Yeah.
Yes.
Generally is. It has to be private, but let me redefine it as private. Okay. I'm combining the two force. So this is something that can be done when you have a parallel construct and a for. You can merge them together into a single liner, and so that you can have things so large, you can actually use this. So we declare shared, private, and how to schedule type. Let's see. I know it's not here. Hold on. Okay. Any problems? And we still have segmentation fault. Threads. What is going on? So it actually is running, but we have, I mean, here J is disabled. I mean, it's not shared among anything. It was initialized. Key start. Let's comment this out. Shouldn't, unless I made a mistake elsewhere. It should work. Yes, there was an error before. So the error before. Where is the error? I don't get it.
What does the compiler say?
Can
Warning.
we check the output? Yes, the output. In which
multi-line comment.
the execution.
Warning, warning. There are warnings, but the error.
Maybe
No, there are no errors.
Output.
No.
Which line is?
It's line 3 of the temporary file, but line 3 is where the .x is. This is the comment that is executed.
Okay.
Segmentation.
This is the comment that is executed.
Segmentation fault is common when we access a location which is
Memory.
not allocated.
Yeah, you might be accessing.
I'm sorry.
Yeah, and then other also bottom.
I'm sorry. This was. Yes.
Did I check before the commenting the other loop?
Yes. No, this one is okay.
Okay.
Oh, there we go.
Good debugging team.
Good debugging team, yes. segmentation fault again. Ah.
Okay.
Let's run. Try with that comment. So the segmentation fault then emerged. Ah, yes, I remember that. Now the segmentation fault comes from this parameter. A million, using such large static variables is static arrays is not allowed in the stack. There is kind of not exactly a limit, but
Oh yeah, there is a limit.
and it tells you that the stack is way too large.
Yeah, there is a
Yeah,
limit.
there's a limit, but there's not necessarily that little. It could be large.
I don't know. No,
Anyway.
the thing is that the limit is posed by, I guess, the designers of the hardware, because or the OS, I don't know, because you have to, I mean, when you have things in the stack, then you have to there are algorithms to organize the memory. But once you go to the heap, then they say, okay, it's your thing. If you, I mean, we will not organize this very good. So these algorithms have some limit. Yeah.
Yeah, so if you see 1 million was okay with one vector, but with 2 vectors and 3 vectors, it's not okay. So
yeah,
10,000 was okay.
In that case, you will have to allocate memory, yeah, in the heap.
Exactly, in the heap. Okay. Okay. So this actually ran very well. 10,000 is okay. It's not so bad. But we won't be able to measure very well performance increases. Anyway, let's give it a try and see if we can measure up the time spent to copy one or to add 2 vectors. Okay. And let me change this. So this is adding V1 and V2. Compile and execute. It's not showing. It's not showing something. It's not showing. It's not printing. Part 2 is not showing anything. Now what is going on? Do we still have problems with memory allocation? I hope not. No. Okay, so the best thing we can do is print out stuff. We comment pragmas away.
I sent to the chat a way to allocate dynamic memory. Maybe it can solve your problem of memory.
Yeah, with vector. I can use the vector memory, vector assignment.
Yeah.
We can use vector instead, just to make it a very heavy load test. Let's give it a try with vector, but
yeah, or you can use also the new C++ way. Yeah.
Okay, so let's go ahead. Oh, you're using a C style allocation, Aurelio?
Yeah, but that's okay. Just don't forget to free the
to
memory.
Import the malloc. Yes, and import the malloc.
Yeah, malloc is the C way.
Yeah.
I mean, in principle, one should, it's safer to use the C++ way with new, but it's also valid.
Null pointers as well. Huh?
These are the kinds of things that you don't have to take into account when you are working with Julia.
Exactly. I mean, I'm boring. I'm bored. let's use vector. Vector is much faster. So it's dynamic allocation, and then let's use dynamic allocation. Oh, hold on.
You want
Yes,
to create a vector of pointers or just a vector of values? Okay.
Just a vector of pointers.
Well, you can do that also.
Oh, we call it decimal. And n.
Yeah.
Same goes for v2 and res. The problem is that we need to also delete the memory.
Well,
and so at the end, we need to place here delete the pointer reference to v1. And we can actually do the assignment of null pointer simultaneously. v2 and res. Okay. Sorry for the problems. We're struggling to survive. Now we can increase this to 1 million. And we shouldn't have any problems because this is actually 8 megabytes. It's very little.
Yeah.
It's very little memory, in fact. Okay, no, it's about 30 something megabytes. But we're still having issues with the print here.
Print?
Yes, this print is not working. Let me comment this out. And let's go ahead. So let's try to wrap up this with this exercise. I'm sorry that we weren't able to finish up with everything that we wanted to finish up. Turns out there are many things to discuss when it comes to
Well, I think it's
openmp.
good for only 3 hours. Yeah.
Yeah, we were tired as well. It's not showing the. I'm a bit frustrated because it's not showing the timer, so we won't be able to measure performance. It's kind of such. It's actually the same declaration. We're making the same declaration. We're starting and stopping and printing, unless this is a double field, but it's not. Shouldn't be. Shouldn't be a problem. Sorry. Line comment. Oh, now it has. 4.24 seconds, milliseconds. So let's increase a little bit. Let's go to 1,000 to 10 million. And we will have something more decent. And this will take a little bit more time. It scales linearly, so it's not that bad. 39 milliseconds. Now we can see what happens when we turn on parallelism. And let's go ahead and do this. So we need to declare the pragmas. openmp parallel for. This start has to be defined before the pragma. Private J. It's instantiated outside and forget about this. Just for the sake of matter, let's compile and run with the -f openmp. And just a small performance increase, not too much.
Yeah, I mean, maybe what operations are you performing there?
Just an addition.
Just an addition. Yeah, I mean, additions are really fast operations, and sometimes one has it hard to justify the creation of threads just to make additions. Yeah.
Yes, but there's another caveat to this. Does anyone care to try to understand? We're making a lot of in-RAM memory reads and writes. You see, the entire vector of 10 million or something sites does not fit in the cache.
Yeah.
So it will take a lot of time to go in and retrieve the portion of the vector that it is working on and then writing it out to RAM and successively. This is also the reason why this is a little bit more expensive. But if, for example, we would like to change this to the dot product, how we would do that? And this is the last comment. So let us think about the dot product. And for our last exercise, so dot product of V1 and V2. Because in this exercise is much nicer. Say we want to store the result into .v1, v2, okay? And we will initialize this variable as 0, and this variable has to be declared as shared. We no longer need res, but what we need is to ensure that we're adding to dot v1, v2, and multiply. So we can actually do it in a 2-stage. So we can define here like decimal temporary file, temporary. Actually do it outside. So it seems like a temporary sum. Better inside the parallel region. No, outside. I don't have time to explain this, but it's better to define it outside. 2, 0, and then declare this variable as private. Okay.
Juan, the time is over, so can we have a little summary of all the things you point out on this presentation, so we can get a general idea for the
yes,
participants?
so that we can. I'm sorry, but there's a lot of material to cover.
Yes.
The general idea that I wanted to express and manifest with openmp are basically that is, first of all, it's not the only threading library or the threading strategy paradigm, but it is one of the simplest and easiest one of them to implement into the code. We might have struggled with some hiccups, but this is part of actually the development of C and C++. You always get segmentation faults. You always get this problems with memory heap and memory stacking, because low level, even though C and C++ is no low level, it's actually high level programming languages, they're very close to machines. So you can get this feeling that you can actually tweak into the little things. But openmp offers you a reliable, a portable way of looking into a threading architecture and implement it into your code and speed things up quite a bit. The other advantage that openmp has versus, for example, other parallelization strategies is that you can actually turn on and off parallelism with just turning on and off a flag at compilation time. So you can always check results. So the testing is done much faster with openmp than with other libraries. Parallel STL is a nice feature from C++ that has recently been incorporated in the last, let's say, decade, but it's still a work in progress. The other advantage that openmp has, and the message that I would like you to learn openmp, not only because it's very simple to implement, it's the fact that it's already incursionating into other devices as well. Not only CPUs, which is the case that we exercised here in this 3 hours, but it also is being capable lately in the API specification 4.5 and 5.0 into devices such as GPUs, FPGAs, etc. That was the message that I wanted to send you. I also wanted to send you a pretty clear message of the different strategies of parallelism. Not only openmp itself, but actually the little diagrams that you now have access to is a way to think of and rethink the way that we program our code, that we write our code, and the way that also we think to solve our problems. The other thing that, well, one last remark is, the best code that is ever written is the code that is the simplest. And that is why this pragmatic approach for openmp, I think it's wonderful, because just in a simple declaration, in a one-liner, you're parallelizing an entire loop that will otherwise require a lot of effort using pthreads or Intel TBB or whatever, what have you. So that's pretty much it. And thank you very much for being with me today. I'm sorry for delaying too much.
Thank you, Juan. I think this talk was very interesting. So I would like to say to all the participants that Juan was showing to us a low level of parallelisms. But as he says, nowadays there are a lot of that hide this complexity. For example, yesterday we saw Dask, and in Dask we don't have to care about how parallelisms is given behind the sense, but in a sense, the parallelisms we have to do is something like the thing was showing us Juan, something like that. On the other hand, there are other tools such as GROMACS or or MATLAB that on that tools you only have to enable parallelisms, and those tools automatically parallelize the code for you. So there are a lot of levels of parallelisms in the tools. So that's all.
That is a good question. That is a good point, Aurelio. But keep in
Yeah.
mind that most of these tools were developed by someone that was actually parallelizing it. So
Yes.
most of those people were using pthreads, OpenMP, OpenACC, or what have you.
Yep.
So thank you very much again, and see you tomorrow.
See you tomorrow. Thank you for your time. And thank you to you, Juan, for your effort and time developing this material.
It's okay. So the materials will be posted in GitHub so that you can access them. And also I will be posting the solutions to all the exercises later on tonight so that you can actually contrast and test out your skills.
Thank you, Juan. Thank you for your nice talk. And so yeah, we will see each other tomorrow. Please, I want to remind you to get your IBM ID if you want to participate on Saturday on the workshop, the morning workshop. So for that, we will use, I think we will get access to IBM's quantum machines. But then if you want to participate, you need to obtain your IBM ID. So please do, so that by Saturday, we will have that. Okay, so thank you again, and see you tomorrow. Have a nice afternoon.